So hi everybody, welcome to my talk today. I'm here to talk about multi-tenancy. Before my talk, I was preparing it and I was like, people want to hear about AI, right? I should try to put it in. I failed. There's too much to talk about in distributed systems and multi-tenancies. If you're here for AI, I don't have any of that in my talk. I'm going to use up all the time. I'm a distributed systems nerd. I came from the world of AWS originally. I started my career building out DynamoDB. That's where I met my co-founder, who was the head of engineering at Dynamo at the time. His name is Quadra. He and I have always been really engaged and intrigued by the whole world of scaling and operating and how to maintain stability at scale. From Dynamo, we kind of parted ways, and he went to run more and more AWS services and launch a bunch of new ones. And I decided to explore the world of startups. So I joined a really small company at the time called Lightstep. I spent over 4 years there helping the company grow and really mature as a business. They're also a distributed company. They are looking at distributed tracing. So distributed tracing, eventually we built out a metrics product. A whole lot of fun stuff, building out our own time series database to serve all the observability metrics that we were getting from our customers. Gave me a whole bunch of startup experience and inspired me to start my own company. At which time, of course, Quadra and I came together and said, why don't we do this together? We have very complementary skills. We both love distributed systems. We want to solve the problem that we see in caching that we solved already, helped solve already at Dynamo for databases. A part of that solution, the center of it, is this idea of multi-tenancy or sharing resources behind the scenes, which actually can sound really scary. A lot of people that I talk to, when they first hear the words sharing resources, they kind of back away and say, no, I don't want to do that, right? Nobody likes doing that. So overall, I feel like personally that multi-tenancy actually has a pretty bad rap. Side note, it's a bad rap, not a bad rep, which I learned when I was making this presentation. It's not bad reputation. There's actually a whole historical context. So I'm using it correctly. It's not a typo. You can look it up after. It's super interesting. But I think that there's a bad impression that the word multi-tenancy gives people. I think it's very accurate from a technical perspective, not so good for marketing, right? Like you hear multi-tenancy, you think of like, some messy resources, messy building. You have to share with other people. You're constantly fighting for a piece of the resource. In reality, I think that there's a lot of benefits that it offers. If you can look behind or look past the fact that it's called multi-tenancy or shared tenancy. And this is what the talk is all about today. Is we'll dig into why I think that it's actually a very powerful concept. And more services than you think use it behind the scenes. Again, it's not a great marketing term, so you don't hear about it. But from a technical perspective, that is exactly what we're going to tackle today. So there's a few areas that we'll go through. This is just like a quick overview, right? We'll go through why I think resource sharing is a really powerful concept that allows innovation to happen. And we'll go through things like robust scaling. Right, how it supports operational stability at really, really high throughput and high scale. And that leads to better availability as a whole, which is really, really important for a software as a service. And we talk about how it really helps from a business perspective. It's not just technically superior in many ways. It makes for a really good business model because of the economies of scale that multi-tenancy offers. All right, so let's first talk about resource pooling. And just to set the stage for everybody, what I mean when I say multi-tenancy, it means that instead of managing individual clusters or individual machines and using that as your isolation boundary, you're managing resources as a pool of water, right? So throw away all the bowls, throw away all the cups. You're putting together all the resources you have and sort of dishing it out as a sort of a shared tenancy model. And that actually allows a lot of powerful things, like I said, to happen behind the scenes. So really, really simple example, and just A lot of AWS services actually operate this way, and that's where I learned a lot of the techniques and some of the tricks behind it, right? So something like, AWS Lambda, really redefining the whole world of serverless computing. They're a multi-tenanted service, and they're able to handle instant scaling and very unexpected spikes on behalf of their customers. And now, there's more companies than you can think that actually runs on AWS Lambda. I recently learned some of the teams on Capital One of the largest financial institutions in the country, run completely serverless on Lambda, right? So the world is really sort of transforming and realizing some of the benefits that they can get when they don't have to worry about managing infrastructure manually. Of course, DynamoDB, right, where I learned a lot of this art, how they can handle, how they grew to hundreds of millions of transactions per second and being able to handle that by basically managing servers behind the scenes on behalf of our customers. So let's look at a really simple example to set the stage for this. So isolated tenants are individual servers that you manage. You can have multiple, but again, the boundary is the physical boundary of the machine, right? Everything that comes to this one machine is isolated to one tenant, and you don't get to scale up or use other machines unless you explicitly make a decision to add more servers. What happens when that happens? Well, then you need to think about this concept of sharding, putting 50% of your data on one server and another 50% on the other server. When you get a lot of traffic, guess what happens? You have two servers, and when you maximize the capacity of those, you're done, right? Unless you do manual scaling, you're not going to be able to get more capacity. So again, in a really simplified manner, if we have 5 servers, TPS stands for transactions per second. Each of them can handle up to 100 transactions per second. And you have a bunch of workload that comes in. It can get distributed over the servers. What happens when one of the servers get more than 100 transactions per second? Everything is well up to 90, up to 100. When you get more than 100, the servers start to time out, right? We've all seen outages, I think, or experienced them firsthand, unfortunately. What happens when you get paged at 3 a.m.? Timeout starts to happen, unexpected errors, performance issues. The server can just go down altogether and be super overwhelmed, whether it's because of memory outage or CPU contention, lock contention, all kinds of problems. So if you add up the top TPS, right? I did the math. Hopefully I did it right. It's 430, right? So what happens is when you look at the individual tenants' peaks that exceed the individual capacity, so the second server from the left, exceeding the capacity by 100 transactions per second. Guess what? There's another server that's barely serving any traffic, right? There's about 90 TPS of capacity in the server next to it. They cannot share that, right? You can't just dynamically move that around. So you have one server that's kind of wasting away its idle capacity while the other server is barely hanging on or already suffering from an outage. So simple idea of the multi-tenancy is from the beginning, instead of treating it as 5 separate clusters or 5 separate servers, you just pull them together and you say, nope, in total I have 500 TPS available to me, and if I get a total of 430 transactions per second, all of them succeed. 100% of them succeed because it's well under. So it's this idea of looking at the individual peaks, and the aggregate of the peaks is still lower than the aggregate capacity that you have behind the scenes. Now, of course, this gets more complex, so we'll talk about what happens and how that gets managed. So what happens underneath the scenes is that by default, when you get to a sufficient scale, so something like DynamoDB table, right? When you go to Dynamo, what are you doing? You're just saying, create a table. So give me a table. Right? It's a logical concept. And this logical concept allows Dynamo to actually transform the physical allocation behind the scenes. So when you go to Dynamo and you say, create me a table, Dynamo spreads that table over multiple servers, right? So in the previous example, they can spread it over 5 machines. But in reality, it's a lot. There are DynamoDB tables with thousands of shards, or you can call them partitions, depending on the term. But really what that means are hundreds and hundreds of servers by default is backed, or one table is backed by hundreds and hundreds of servers. So this logical concept to the customer is this one table, but behind the scenes, physically, it's actually peanut buttered over many, many different servers. what does that allow us to do in production at scale? Well, when you're running at low traffic, each of those servers is barely moving, right? It just has to work a little bit to serve that low traffic because it's spread over, like, let's say 100 servers. Now, all of a sudden, let's say an event happens, right? So for Amazon.com, that's something like Prime Day, right? On Prime Day, they get at least 10 to 20x more traffic than they do on an average Wednesday. So when Prime Day happens, now the traffic, 10x's, 20x's, 100x's, now all the 100 servers has to do is they just have to work a little bit harder, right? Because you have this pooled resource, and each of them just has to come in and work a little bit harder. So let's say, let's do some math here, and then keep me on it. So, usually you have 100 transactions per machine, right? And let's say you have 100 of these, and usually you get very, very low traffic, so barely any transactions hit each of these machines. All of a sudden you need, 5,000 transactions per second, right? It's like a vast increase from usual. All it has to do is that each of these machines has to contribute, 50 transactions per second, right? 5,000 divided by 100. So that's well within what they're rated for, right? They're rated for 100, you're contributing 50. So that to Dynamo, to the customer, what are they doing? They're going from maybe 10 transactions per second to 5,000 transactions per second. What is that, like a 500x, right? That's a pretty big peak, right? Look at your own traffic. If you look at your baseline, you look at your peak, like, can your systems usually handle a 500x spike? A lot of systems cannot, no matter how much time you put into sort of provisioning and planning it. And by the way, you also got to benchmark it, right? Because imagine if you're not using a managed service, you don't know whether your services can handle a 500x increase in traffic. You got to create your own infrastructure to even simulate that kind of scenario. Dynamo has done it. Multi-tenant services has usually done it because guess what? If you think you have a lot of peak traffic or bursty traffic, someone else has had something bigger. So that's kind of how we modeled after a lot of the multi-tenanted services, and we feel like that offers more robust scaling as a result. And we've in fact seen it for customers. So better availability, right? So more robust scaling is one, but more robust scaling is usually the difference between having an outage and not having an outage, which is certainly important. But let's assume that there is no outage. The next step forward is having the same consistent performance, right? So this is a difference between Amazon.com being down, which is catastrophic, but Amazon.com being a little bit slower on Prime Day, which is also pretty disastrous because, people have measured on retail websites for every 100 millisecond delay, however many millions dollars get lost because people change their minds or they get impatient and they get distracted by the next sale, right? So this is the kind of thing that, like, after you can ensure that the scale is handled, then you got to look at performance. And to us, for multi-tenanted systems, performance is one of the most studied subjects, right? Again, when you pool these resources and you have sort of dedicated engineers to work on these problems can get better characterized and they can get better improved at the economy of scale level. So what does this really mean? It means that we look at things like what is the performance at 5,000 TPS, and what is the performance at 10 TPS or 50 TPS, and we ensure that whatever performance you get at low scale, you can expect to get it at high scale as well. That's a really powerful concept. Remember what I just talked about in terms of benchmarking infrastructure? It is really difficult for Amazon to simulate the amount of traffic they get on Prime Day, right? Like, how are you going to simulate tens of millions of people being on your website at the same time? It costs a lot of money if it's even possible to do, right? They don't have to do that, right? If they use, and they do now, they do. They used to use, sort of more legacy software, Oracle, but now they use Dynamo. If they just benchmark Dynamo at a lower TPS, Dynamo as a service guarantees that they're going to see very similar performance if they get 500x more traffic. That's a really powerful concept, and I stole these graphs or borrowed these graphs. It's sourced from the Dynamo paper that was recently published, right? So, very quickly, how do you interpret these graphs? Well, at the very left in the blue bar are the performance represented at 100,000 TPS. 100,000 transactions per second or ops per second. You can see that that's what Dynamo considers to be a low workload. 100,000 is their starting point. And then at the very right, in this like darker yellow color, is the performance at 10x that, which is 1 million operations per second. And the y-axis is not labeled because it doesn't matter, it's all relative. The y-axis is the performance or the latency of reads and writes at that workload, right? You want to see this flat line. You actually want it to be as flat as possible, but you can see it's pretty much within the same range, meaning that Dynamo has done a lot of characterization and work on their part to say, hey, we can operate consistently at 100K ops per second or 1 million ops per second. And this is pretty powerful because a lot of systems tend to break at peak loads. But peak loads for businesses is when they make the most money, right? So there's this dichotomy where you want your system to be as popular as possible, but you actually have never stressed your system to that point because it's difficult and expensive to stress. One of the sort of interesting anecdotes here that I'll take an aside to talk to you guys about Twitter. So we actually partner with Twitter a lot, not as a customer, but they have an internal caching team that we borrow a lot of experiences and we exchange a lot of notes. So I think it was like 2014, one of the Oscars, Ellen DeGeneres took a selfie. It's like the selfie of the century or whatever, where she asked like the public, she tweeted the selfie with a bunch of Oscar nominees and Oscar winners, and she asked everyone to retweet and like it and break the Twitter record, right? This happened in 2014. I happen to know the lead principal engineer on that caching team. When that happened, the entire team was up for hours trying to fix Twitter because it caused an outage. And that's because of a caching issue. The counter on that tweet is on one machine, right? So you can imagine all these millions of users coming in, liking and retweeting, and that machine just cannot handle it. What happens when that machine goes down? Well, the data, they have some rotation. Another machine comes up, starts serving the same counter, brings that one down, right? We call this cascading failure in distributed systems. So that's one of those exact scenarios where that's Twitter's shine moment. That is Twitter's sort of, one day of fame where everybody's on Twitter trying to like this image, and it's not working, right? So that's what I mean by it can be really catastrophic because the one day or the 1 hour where you really need your application to be working, it's not, because you're not able to simulate it at that scale. And multi-tenant systems sort of give people an opportunity to really serve the public at a big enough scale that you're pooling all the resources and you're spending a ton of time. Like when I worked on Dynamo, the amount of load testing, benchmarking that we do at a scale that we haven't even seen before because we know one day a customer will get there, it's kind of insane. But anyway, let's move on to talk about cost a little bit. Sorry, just use this. Yeah, so a lot of what I've talked about so far is what customers care about as an end user, right? Like why should I not be scared of a multi-tenanted system? How are you guys better at distributed system than I would be if I was managing my own machines? As a business, I think it's helpful to also think about like why anybody would be interested in taking on all these problems, right? So the economy of scale is a really powerful concept. We talk to a lot of customers that have this concept of, at Amazon, we call them 2 pizza teams. At other companies, I think they just call them mini startups within a big company. So, this concept of having a really large company, I have a friend that works as an engineer at, Headspace, right? They have many, many different teams, like over 100 teams. And then each team manage their own sort of little startup. So they have their own resources and they manage their own budget. And then you go talk to each individual team, they're spending what? I don't know, maybe $10,000. Don't quote me on this, it's not real, I'm just making up numbers. But $10,000 a year on their infrastructure at this company, XYZ or Headspace. Nobody's gonna spend any engineering resources to optimize $10,000 because the most you're gonna get is a few $1,000s, and the opportunity cost engineering time is very valuable and very expensive, right? Now you multiply that by 100, let's say there's 100 teams. all of a sudden you're at what, like $1 million per year, right? If you pool these resources together and you're looking at your bill and you're spending $1 million per year, is it worth spending a couple of sprints to maybe bring that down by a few $100,000? Maybe, right? Even at the team level, if you were able to optimize by 50%, lowering your bill from 10,000 to 5,000 is not really worth anybody's time. No engineers love cost optimization, right? When you pull it together, then all of a sudden you get more motivated to optimize, because any incremental percentage savings ends up being actually a lot of dollar signs. So that's sort of why, as a business, it makes sense to manage machines or manage services like caches together. And then when you think about this other concept as a business, you can get into oversubscription. This happens in the real world all the time, right? So oversold flights. All of us, I think most of us has been through one of those where they sell more tickets for this flight than there are seats on the plane, because they're banking on the fact that not everybody's going to make it. Gyms, right? Very famous for this. They oversell. They sell a lot of memberships. Most people don't show up. If everybody showed up at the same time, they'd be in trouble. Bank runs, same, right? Like, banks reinvest your money, right? That's how they stay in business. But if all of us went to the same bank at this, I mean, this happened in Silicon Valley Bank last year. Everybody's familiar with this. So, like, you know, this oversubscription idea is really powerful, and everybody uses it in the real world. And guess what? It's just all a statistical game. It's fine. It sounds scary, but to the individual user, it normally 99.99% of the time does not impact your actual use case or workload, because you're not going to show up. Again, like, very, very rarely is everybody going to show up and ask for the same thing at the same time. And there's you don't have to read the whole thing, but there's a famous quote from the AWS Lambda team in a paper that they call Firecracker that's also published on this exact idea, and how this allows many, many services and many of our, you know, electrical systems and you know, airplanes, allows them to make money and be profitable, because they can sell more of their services than they actually need to serve. So as a business, it makes a ton of sense without actually having, you know, that much negative impact, or if any at all, right? Now, you know, you can argue that for some companies like airlines, they do it too often, and then they have to, you know, work themselves out of trouble. At the software as a service, we have to modulate how aggressive we are with oversubscription. All right, how am I doing for time? Okay, awesome, thanks. So that's the first half of the talk. We sort of talk about, well, all these benefits, you know, better scaling, better availability, more robust, and economy of scale. I want to take sort of the last bit of the talk to talk about, well, there has to be a reason that people don't like sharing, right? There has to be a reason that there's such a bad rap, or it has a bad reputation. And it's because of this noisy neighbor problem, and the fact that humans have this selection bias or confirmation bias, right? So if one person tells you about this noisy neighbor issue that they've been having with their stack, it makes an impression. Next time you see a problem that sort of resembles the shape of what they're talking about, you're going to attribute it to the fact that, oh, it's a noisy neighbor problem. Oh, that's because I'm using a multi-tenanted service. And if I didn't use a multi-tenanted service, I wouldn't have any of these noisy neighbor issues where people are fighting for the same resource and someone else's workload is impacting yours, and that's really annoying. I wish I had my own resource, right? So it's a very common, what I think is a misconception, because if you dig in a little bit, this noisy neighbor problem always exists, right? Unless you can guarantee that you literally, and we used to have this, right? You literally have your own server rack. And by the way, that server rack also can't share network bandwidth, because if you share network bandwidth with other people, you can run into a noisy neighbor issue, right? I mean, telecom companies run into this all the time. That's why we all have limits on our upload and download speeds. That's why you pay more for more speeds, right? They also deal with this, like, resource allocation sharing. And the truth is, single tenanted systems are noisy as well, right? So whether it's a database cluster or a caching cluster, we deal with this a lot at Momento for caching clusters. We hear this story a lot where, usually, let's say you want a single tenanted resource, right? You don't want to share with anybody. So your team has your own like cluster. And your team usually has multiple people. Multiple people, guess what, work on multiple projects, different projects. So then you have this concept where, let's say you have a cluster, you're using it, and you're running some load tests or benchmarks, and it's performing perfectly, and it's very, very stable, and all of a sudden performance tanks. Well, what happened? Well, your colleague didn't know, and they're using your team's cluster for some expensive scan operation, and that's impacting your performance. So what happens in real life? You go and you ping them, and you say, hey, can I have my cluster back for 9 to 5 today, and you can use it tomorrow, right? So like this kind of resource allocation and sort of isolation, where you're working out the fairness, like I get it today, you get it tomorrow, and that way we don't have to impact each other. That happens in real life as well. You're just moving from the noisy neighbor problem for being resolved at the machine level in an automated way, which for multi-tenant systems, that's what we have to do. We have to find some way of maintaining fairness so people don't interfere with each other. You're moving that into real life where you're having to kind of acquire a lock on it. I've worked on teams where instead of pinging the person, we create some sort of like, a spreadsheet, right? So you go and you reserve the instance for a certain amount of time. So this happens all the time. It happens in prod, right? So your prod system can be running perfectly, and then somebody comes in and they want to do a little bit of debugging or analytics, and they run an expensive command without realizing it's expensive, and that tanks your cluster's performance. So anyway, my point is this noisy neighbor issue nowadays, unless you really have your own data center racks, which a lot of companies still do, but for those of us that live in the cloud, everything is shared, right? You get an EC2 instance, it's shared, right? You can get a metal instance, that's probably not shared. But again, the racks are shared, the network cards are shared. So everything is multi-tenanted to a certain level. It's just, is it at a level where you understand and you have visibility into it? So it's a problem that needs to be resolved regardless. And for me, not having to go ping my colleague is better than, not having to go and do that. Like I'd rather not deal with that kind of human-to-human interaction. It's better to automate it with machines, right? So some of the common techniques that we've implemented and sort of had to deal with, and this is an evolving process, right? It's not just like 3 magic bullets and it solves all your noisy neighbor issues. But this is a start, right? So the foundations of mitigation, the very first one is definitely load balancing, right? So behind the scenes, we're still managing many, many servers, and you want to make sure that the servers are about equally busy, right? When you run into issues is when you have one server that's overwhelmed. I talked about this at the very beginning of my talk, right? You don't want some boxes X'd out and other boxes are sitting there kind of, just chilling. So load balancing is really important. And load shedding, right? So when a machine gets really, really busy, the best thing it could do is quickly tell the sort of apply pressure downstream to say, no, go find another box, I'm too busy. Prioritizing request handling and controlling bursting. So to go back to my example, thinking about requests that come in very, very quickly all at once is very different than requests that are sort of very, very nicely distributed. So a technique that's commonly applied here is you throttle them. You tell them, no, I'm too busy, you can come back later, and then usually there's something kind of like default retries that's built in with backoff or something. So the retries essentially, they get rejected the first time, they retry again, and that is basically a way for the server to help spread out the traffic a little more evenly. This is something that we actually ran into maybe a few months ago, right? So we, at Momento, we started by measuring things at a granularity of a second. Pretty common, right? So we throttle at the second level, right? So if a customer comes in, they're a new customer, they're not paying us, we have a default limit. Default limit something like 1,000 transactions per second, that's what you get. And customer comes in, throws us a few hundred below the limit, a few hundred transactions per second, they get throttled. And they shouldn't. We dig into it and we're like, what's happening, right? You haven't reached 1,000 transactions per second. We dig in and we implement all these methods. We get our performance engineers take a closer look, and we suspect that the granularity of our metrics need to be finer than a second, right? So we install all these tools, we finally measure it, And then we're able to see it at the sub-second level. And then you can see that this customer is sending us all of the requests within the first 100 milliseconds of that second, right? So really, if they're sending us something like 200 transactions per second, because that's all we were able to see is that there were 200 transactions in that 1 second. In reality, they're sending us that 200 transactions in the same 100 milliseconds. And then for the 900 milliseconds is completely idle, nothing, right? So it's not evenly spread within that second. And if you really think about it that way, it's as if they're sending us, what is it, like 200 times 10, it's as if they're sending us 2,000 requests per second, which is well above the default limit of 1,000, right? So it gets very nuanced, is my point. It takes a lot of digging, a lot of benchmarking, a lot of learning. And these lessons that we learn can hopefully be forward applied to our future customers to do even more work on fairness and isolation. With this customer, it was as simple as adding a little bit of jitter in their server so that they're not like all hitting our service at the same time and causing our service causing too much burst, and then they have to get throttled. Global admission control, so very similar to what I just talked about. This concept of throttling at the logical level is really important, right? So going back to my example, when you come to DynamoDB and you create a table, we create it automatically on multiple servers. Now, if we were throttling at the server level, then what happens, because we're putting many, many customers spread across like 5 servers, right? So on each server, you're actually serving multiple customers. So if you're throttling at the physical node level, you're going to impact multiple people. That's not OK, right? You're going to sort of increase your blast radius. So this idea of distributed throttling, so that you're throttling at the logical level, so that customer A and customer B, if customer A is the one that's causing you issues because they're sending you a lot of traffic, you want to throttle them across the board on their tables only, right? So this means you're doing a little bit of sort of fine-grained throttling on each node, but only for that customer, right? Only at the logical level. And this is an important concept so that you can make sure that one customer doesn't impact all the other customers on the same node. They just impact themselves because they're the bad actors, right? Most of the time it's inadvertent bad acting, but still, you want to be able to protect other customers. So anyway, to wrap it up, multi-tenancy fuels innovation. I think it enables more robust scaling. We've seen this live at Amazon and with some of our customers at Momento with something like Paramount, right? We serve some of their biggest sports games, and they're able to go to 10x, 12x their peak load because of this idea of robust scaling. And as a result, they yield better availability, better performance, and it's more cost efficient. So I do think that it's still a bad marketing term. There's a reason that you don't really hear about it in a very positive connotation. I like to think of multi-tenancy as really like what's popular nowadays or trendy is like ecotech, right? So it's both ecological because it saves energy, it eliminates waste, you're not having as many idle instances lying around, and it's very economical, right? I talked about the economy of scale. So I do think that, I'm not a marketer, but I was trying to think about how to describe it better. And I think ecotech is a pretty interesting way to think about multi-tenancy. Thank you.